What if the universe is even bigger than we ever imagined? Somewhere, 3 billion light-years from Earth, lies a structure so massive, it bends our understanding of reality. It's not a black hole, not a galaxy, not even a cluster of galaxies. It's something far larger, something that changes the very map of the universe. This is the story of the Einasto Supercluster and why it is rewriting everything we thought we knew about cosmic size. Chapter 1. The known giants of the universe. Let's begin with what we thought we knew. For decades, astronomers believed that the largest structures in the universe were galaxy clusters, massive collections of galaxies, held together by gravity. Each cluster can contain hundreds or even thousands of galaxies, floating in a sea of dark matter and superheated gas. These clusters, while gigantic by human standards, turned out to be just the building blocks of something far more immense. The most well-known of these is the Einasto Supercluster, our cosmic home. Discovered in 2014, Einasto means immense heaven in Hawaiian. It spans more than 500 million light-years and contains over 100,000 galaxies. That includes our Milky Way. For many years, Einasto was the largest, clearly defined structure we knew about. It became a symbol of just how small our galaxy really is in the grand scheme of things. But Einasto was only the beginning. Beyond it, astronomers began to detect hints of even larger structure, walls of galaxies stretching like cosmic highways across the universe. These were not superclusters in the traditional sense. They were something stranger, enormous sheets and filaments connecting clusters together in a vast web. One of the most famous is the Sloan Great Wall. Discovered in 2003, it stretches 1.37 billion light-years across. At the time, it was thought to be the largest structure ever found. Then came the Hercules, Corona Borealis, Great Wall detected through gamma-ray bursts. Some astronomers believe it may be as long as 10 billion light. That's nearly the size of the observable universe itself. But here's the catch: it's so big and so far away that its true nature is still debated. Is it a real structure or just a coincidence in the data? This is where things get complicated. When we talk about size in the universe, we're not always talking about something solid. We're describing regions of space where matter galaxies, gas, dark matter clusters more densely than elsewhere. And the farther away we look, the more difficult it becomes to say whether these structures are actually connected or just appear to be from our point of view. That's why scientists began to question, what is the true scale of structure in the universe? How big can it get before gravity is no longer the main force holding it together? This question led to one of the biggest discoveries of the 21st century. But to understand why it matters, we have to go back to the way we map the universe. Astronomers use something called redshift to measure how far away galaxies are. Light from distant objects is stretched as the universe expands, shifting it toward the red end of the spectrum. By measuring this redshift, scientists can create 3D maps of galaxy positions across billions of light. These maps are not random. Instead, they reveal a paternal web of filaments and voids. Galaxies tend to form along thin threads of matter, while vast empty regions stretch between them like bubbles in foam. This pattern is known as the cosmic web. It's the largest known structure in the universe, but it's not a single thing. It's the overall shape of everything. In this web, galaxies are like dewdrops hanging on invisible threads of dark matter. Clusters sit where filaments intersect, and superclusters are the dense nodes where multiple threads come together. Over time, astronomers began to identify and catalog these There's the Shapley Supercluster, rich with thousands of galaxies. There's the Coma Supercluster, near the direction of the constellation Coma. Each one tells a different story about the universe's structure and even. But as our technology improved, and as sky surveys became more detailed, astronomers began noticing patterns that didn't quite fit. Some regions seemed too dense, some clusters seemed to align, and some structures stretched so far that they broke the theoretical limits of what gravity should be able to hold together. This is known as the homogeneity problem. According to the cosmological principle, the universe should look roughly the same in every direction at a large enough scale. But these massive walls and chains of galaxies were starting to challenge that idea. Are we seeing actual structures that defy physics? Or are we seeing illusions caused by perspective, data limitations, or cosmic coincidence. This debate reached a peak in the early 2020s. New surveys like the Dark Energy Survey, the Euclid mission, and the James Webb Space Telescope started returning deeper, more accurate data. And in that flood of information, researchers began to find hints of something new, something that wasn't just big, but fundamentally different. They called it the Einasto Supercluster. At first, it didn't seem like much, just another clump of galaxies. But the more they studied it, the more it stood out. It wasn't just its size, it was its shape, its mass, and its location in the universe. It didn't fit neatly into any category we had seen before. Unlike Laniakea, which is relatively diffuse and still not fully gravitationally bound, Einasto appeared to be denser, heavier, and more cohesive. It stretched across hundreds of millions of light, and its estimated mass was staggering, over 26 million billion times the mass of our Sun. To put that in perspective, that's more than 10 times the total mass of Laniakea. And it wasn't a wall or a shit, it was a supercluster in the truest sense, a knot in the cosmic web, so massive that it could influence the motion of galaxies hundreds of millions of light years away. What made it even more compelling was the name. The structure was named in honor of Einasto, the Estonian astrophysicist who helped pioneer the modern understanding of dark matter and galactic distribution. In many ways, the supercluster was the physical embodiment of his life's work, a giant made of galaxies, dark matter, and gravity. It's poetic, isn't it? The man who helped us understand the invisible forces shaping the universe now has his name tied to one of its most astonishing structures. But the discovery of the Einasto Supercluster wasn't just a tribute, it was a turning point, a signal that maybe our maps are still incomplete, that maybe we've only just begun to grasp the true architecture of the cosmos. In the next chapter, we'll dive into the discovery itself, how scientists found Einasto, why it took so long, and what it might reveal about the invisible scaffolding of our universe. Because when you find something this big, you can't help but wonder, what else is still out there? Chapter 2, The Discovery of the Einasto Supercluster. It all began quietly. No headlines, no fireworks, just another batch of data millions of light years away waiting to be interpreted. The universe hides its secrets well, but it also leaves patterns. And some scientists are especially good at noticing them. In early 2024, a team of astronomers from the Tartu Observatory in Estonia was combing through redshift data from several galaxy surveys. These surveys, compiled from instruments around the world, mapped the locations and movements of galaxies across the sky. Most of the time, the data revealed what scientists expected. Clusters here, voids there, the familiar spiderweb of cosmic filaments, but this time, something stood out. There was a dense, elongated Regina thread of galaxies stretching across a vast swath of sky, about 3 billion light-years away. Not just one cluster, not two, but dozens, connected, aligned, and too coherent to be a coincidence. It wasn't in the existing catalogs. No known structure matched it. At first, the astronomers thought it might be a data artifact, a mistake in the observations. So they double-checked everything. They looked at surveys from different telescopes, different wavelengths, different sky maps, and no matter where they looked, the shape remained, like a scar on the cosmic fabric, quiet, distant, and impossibly vast. They called it the Einasto Supercluster. The name was chosen not just for its location or its mass, but as a tribute. Einasto, the astrophysicist from Estonia, had spent his life developing models of dark matter, galaxy evolution, and the large-scale structure of the universe. He was one of the first to propose that galaxies do not float alone in space, they form part of a much larger pattern shaped by invisible forces. Naming the largest supercluster yet discovered after him wasn't just fitting, it was perfect. Now, let's talk about how they found it and why it's so special. Most cosmic structures are discovered through redshift surveys. These are like 3D maps of the universe. Imagine you're flying through space, and every dot you see is a galaxy. The farther away the galaxy, the more its light is stretched by the expansion of space. That stretch called redshift tells us how long its light has been traveling. When you plot thousands, even millions, of galaxies by their redshift and position, you start to see patterns, not random scatter, but structure, thin filaments, dense knots, empty bubbles. This is the cosmic web. The Einasto Supercluster first appeared in the data as an unusually long, bright thread in this web. The team noticed that galaxies in this region weren't just near each other in the sky, they were close in space, too. They shared redshifts, velocities, and spectral characteristics. In other words, they were part of the same gravitational family. The structure spanned over 1.2 billion light-years, about 3 times the length of Laniakea. It was dense, more galaxies, more mass, more gravitational pull. Estimating the total mass wasn't easy, but by analyzing the velocity of galaxies, how fast they're removing due to gravity, the team calculated that this supercluster contains the equivalent of over 26 million billion solar masses. That's more than 10 times the mass of the Milky Way's entire neighborhood. Even more fascinating was how it fit within the surrounding cosmic web. It wasn't a random wall. It was like a central spine in a much larger network, connecting smaller clusters and drawing them together, like a cosmic river, gathering tributaries. This made scientists wonder, is this just a or is it part of something even bigger we haven't fully seen yet? But why didn't we see it earlier? The answer lies in observational limits. Einasto is far around 3 billion light. Light from its galaxies has been traveling toward us since early in the history of our universe. That distance makes detection difficult. Galaxies appear faint, stretched, red. Their light is easily drowned out by noise, by dust, by cosmic interference. Also, large structures are tricky to see unless you're looking for them specifically. The cosmic web doesn't light up like a neon sign. It has to be reconstructed piece by piece. The farther out you go, the fewer data points you have. Without detailed, deep sky surveys, superclusters can hide in plain sight. What made the difference in 2024 was the combination of data sources. The team didn't rely on just one survey. They stacked data from several: the Sloan Digital Sky Survey, the Dark Energy Survey, the Baryon Oscillation Spectroscopic Survey, deep photometric surveys from pan-stars and others. By layering these data, they created a sharper picture, like combining multiple exposures to reveal a faint star. And then it appeared, not just a pattern, but a structure. The team presented their findings at an international astronomy conference. The response was a mix of wonder and skepticism. As always in science, big claims demand careful proof. But as other researchers dug into the data, confirmations started to roll in. Independent teams found the same alignment, the same dense galaxy counts, the same velocity flows. Piece by piece, the structure became undeniable. So why does this matter? It's not just about finding something big, it's about what it tells us about the architecture of the universe. The discovery of the Einasto Supercluster challenges some long-standing assumptions. One of them is the cosmological principle of the idea that the universe is roughly the same in every direction at large scales. If structures like Einasto exist in one part of the universe, are there others elsewhere? Are we living in a universe more structured than we thought? Another implication involves dark matter and dark energy. Superclusters don't form by accident. They are shaped by the invisible scaffolding of dark matter mass we cannot see, but can measure by its gravitational effects. And their growth is slowed, even halted, by dark energy, the mysterious force driving the universe's expansion. Finding such a massive and cohesive supercluster so far away means our models of structure formation might need adjusting. Perhaps matter clumps faster than we thought. Perhaps dark energy's influence varies with location. Or perhaps we still don't understand what these forces really are. The Einasto Supercluster is not just a new dot on the map. It's a signal that there's more to discover. In the next chapter, we'll explore what makes Einasto different from all the other superclusters we've seen. Its shape, its mass, its gravitational influence, and the strange ways it bends our understanding of cosmic scale. Because when you find something this massive, so far from home, you start to ask, how much more is hiding in the dark? Chapter 3. What makes Einasto so special? Let's pause for a moment. You've heard of massive things in space before. Black holes, galaxies, clusters of galaxies, even so what makes the Einasto Supercluster stand out? Why is this discovery different? Why are astronomers across the world rethinking what they thought they knew? The answer lies in three key features: density, cohesion, and structure. Let's take them one by one. 1. Density. Not just large, but heavy. Most superclusters we've studied, like Laniakea or Shapley, they spread across hundreds of millions of light-years and contain thousands of galaxies. But many of them are relatively loose. Their galaxies are drifting, not tightly bound. Imagine a fog of islands in the ocean rather than a continent. Einasto is different. It isn't just large, it's dense. Galaxies aren't just scattered loosely, they're packed into a thick central spine that holds incredible gravitational weight. Based on current estimates, the Einasto Supercluster contains over 26 million billion solar masses. That's not just a big number, it's a number that breaks expectations. To visualize it, imagine stacking 26 million billion suns. Or, to bring it closer to home, it's over 10 times the combined mass of every galaxy in our own Laniakea. This kind of mass doesn't just sit still. It pulls, it bends space, it drags galaxies into motion. The gravitational effect of Einasto may reach far beyond its visible edge, influencing nearby clusters and even redirecting galactic flows. This level of density makes Einasto one of the most gravitationally dominant structures ever found. 2. Cohesion. A supercluster that holds together. Most superclusters are temporary. They look connected, but they're not fully gravitationally bound. Over billions of years, cosmic expansion will tear them apart. Galaxies will drift, filaments will stretch, and the connections we see today will vanish into deep space. But Einasto might be different. According to recent simulations, the central region of the Einasto, that means it's not just a temporary gathering, it's a lasting structure, a single dynamic system. Why does this matter? Because the universe is expanding, and at large scales, that expansion overpowers gravity. Only the most tightly packed structures survive the pull of dark energy. The fact that Einasto seems to resist that expansion, at least in part, suggests a critical mass threshold we didn't expect. It's a kind of cosmic anchor in an otherwise stretching cosmos. In the future, when most of the universe becomes dark and empty, isolated by the accelerating expansion, Einasto may still exist as a self-contained island of galaxies, a fossil of the early universe, holding its shape while everything else drifts apart. 3. Structure. A spine in the cosmic web. When scientists first mapped Einasto, they noticed something unusual about its shape. It wasn't a blob, it wasn't a wall, it was thread-like, stretching across more than 1 billion light-years, with clusters arranged like beads on a string. This shape is important. It tells us something about how the universe formed. According to most models, the universe started with tiny fluctuations in the density of matter, small wrinkles in the fabric of space. Over billions of years, gravity amplified those wrinkles into filaments, walls, and nodes. Galaxies formed where the matter pooled, clusters formed where filaments intersected, and superclusters grew in the densest spots. Einasto seems to sit at the intersection of multiple filaments. It acts like a backbone, not just a destination for galaxy clusters, but a kind of cosmic hub where threads of matter converge. Its shape may also reveal hidden dynamics of dark matter, the unseen substance that makes up over 80% of the universe's mass. If dark matter filaments are real, structures like Einasto may trace their skeletons. In this way, studying Einasto could help us map the invisible architecture of the cosmos. The dark matter connection. Jan Einasto the man was one of the first to propose that galaxies Dante have enough visible mass to hold themselves together. He suggested that some invisible material, what we now call dark matter, must exist, acting as a kind of gravitational glue. Naming the supercluster after him is more than symbolic. This structure is a testament to his theory. It may be one of the clearest examples of dark matter at work on a grand scale. Without dark matter, the galaxies in Einasto would simply drift apart. With it, they lock into place, held together by an unseen, powerful force. It also helps us measure the distribution of dark matter. The more mass we can detect indirectly through galactic motion, the better we can estimate how dark matter is shaped, spread, and behaving across billions of light. Einasto, in this sense, is a laboratory, a place where theory meets observation. Implications for cosmology. The discovery of the Einasto Supercluster doesn't just add a new pin to the map, it challenges the scale limits of cosmic structure. Until recently, most cosmologists believed that the universe became homogeneous at around 250 million light. That is, if you zoomed out far enough, the universe would look the same in all directions. No clumps, no patterns, just a uniform spread of galaxies. But structures like the Sloan Great Wall, Hercules, each new discovery adds complexity, depth, and sometimes contradiction. Are we seeing real structures that span billions of light years, or are we mistaking chance alignments for patterns? Einasto adds weight to the idea that the universe is more structured than we thought, that it may take much longer to become truly uniform. And if that's true, then the early conditions of the cosmos were more uneven, more active, more creative than our models assumed. This is not just a story about size, it's a story about origins, how matter organized itself, how structure emerged, and how galaxies like our own came to be. Looking ahead, Einasto is still being studied. Its true mass, reach, and internal dynamics are still under investigation. New surveys will refine our understanding, and perhaps, in time, we'll find even more massive or more complex. But for now, it stands as a kind of cosmic landmark, a structure that defies expectations and demands we look deeper. In the next chapter, we'll explore what this discovery means for our understanding of the universe as a whole. How does Einasto fit into the cosmic web? What does it tell us about the future of structure, gravity, and space itself? Because if something like this can exist, what else might be waiting just beyond the edge of what we can see? Chapter 4. Rethinking the cosmic map. Every time we discover a new structure in the universe, something shifts, not just in the data, but in our perception. It's as if we've been walking through a familiar forest, only to realize that trees are part of a much larger mountain range we've never seen before. The discovery of the Einasto Supercluster is exactly that, a shift in scale, and with it, a shift in meaning. So what does Einasto change? Let's begin with the cosmic map, our best attempt to chart the universe at the largest scales. The old map, a uniform universe. For decades, cosmologists believed in a principle called cosmic homogeneity. It's a simple idea. Zoom out far enough, and the universe should look the same in every direction. Like mist from far away, all the clumps and gaps should blur into evenness. No special places, no preferred directions, just a smooth distribution of galaxies. This idea was foundational. It made the math of the Big Bang work. It helped explain the cosmic microwave background, the leftover radiation from the universe's origin, and it matched most of what we saw, at least until the early 2000s. But slowly, the maps started showing rough edges. Astronomers began finding structures that seemed too big to fit: the Sloan Great Wall, the South Pole Wall, the Hercules, Corona Borealis, Great Wall, and now, the Einasto Supercluster. These weren't just blips. They were organized, galaxy clusters moving together, filaments connecting, masses that stretched across more than 1 billion light. According to traditional models, structures this large shouldn't exist, or, if they did, they should be rare, isolated, and statistically unlikely. Yet here we are, the new map, a web of surprises. With every discovery, the cosmic map has become less like a smooth fog and more like a vast web, pattern full of nodes, strands, and voids. Think of it like a spiderweb made of light, where galaxies sit at the intersections and dark matter forms the invisible threads in between. Einasto is one of those intersections. It's not just floating alone in space. It's anchored, connected to filaments, surrounded by smaller clusters, drawing matter in from multiple directions. This kind of structure suggests a universe that is deeply organized, shaped by ancient flows of energy and gravity. But here's where it gets even more interesting. A challenge to the cosmological principle, the discovery of large, coherent structures like Einasto forces cosmologists to ask a hard question. Is the universe really as uniform as we thought? If a supercluster like Einasto spans over 1 billion light years and has a strong gravitational core, then the assumption that everything evens out at large scales may no longer hold. This doesn't mean the Big Bang model is wrong. but it might mean we need to refine our understanding of how structure forms and evolves. For example, could certain regions of the universe have formed earlier or faster than others? Could there be natural variations in density that shape galaxy formation in ways we haven't fully grasped? Or, more radically, could the early universe have had a set of directional preferences that later grew into the massive structures we see today? These are open questions, and Einasto had placed them front and center. Gravity versus expansion, a battle for structure. Another idea under pressure is the balance between gravity and expansion. After the Big Bang, the universe expanded rapidly. Gravity pulled matter together into galaxies and clusters, but the expansion kept pushing everything apart. Eventually, a strange force, dark energy, took over, accelerating the expansion further. Today, dark energy makes up about 68% of the universe. It's the dominant player, driving galaxies away from each other faster than ever before. So here's the puzzle. If expansion is winning, how did something as massive and tightly packed as Einasto form and stay together? The answer may lie in timing. Einasto might be a fossil of an earlier time in the universe when gravity still had the upper hand. Formed in the densest pocket of matter, it grew quickly, pulling in galaxies before dark energy could tear them away. Its core may have reached gravitational cohesion early, making it resistant to the universe's stretching. This idea reshapes how we think about when and where structure is possible. It suggests that some regions of the universe may still be growing even as others drift apart into cold isolation. Einasto and the shape of the invisible, perhaps the most profound implication of the Einasto Supercluster, is what it tells us about dark matter. We can't see dark matter directly, but we can infer its shape by observing how galaxies move and how light bends around massive structures. In that sense, Einasto is like a fingerprint of the invisible. Its mass, density, and cohesion point to a massive reservoir of dark matter, holding it all together. This gives scientists a rare opportunity to use a real, observable structure as a model for dark matter behavior. By studying Einasto's gravitational pull, we can test theories about dark matter distribution, interaction, and it's not just about size, it's about structure, revealing the hidden framework of the universe. The map is still incomplete even now. Our map of the universe is mostly blank. Most galaxy surveys cover only small fractions of the sky. Some regions, especially far away ones, remain unknown. Cosmic dust blocks our view in many directions, and the farther out we look, the fainter everything becomes. So when we discover something like Einasto, we have to ask, how many more of these giants are out there? If Einasto exists in one direction, might there be others in places we haven't looked yet? Is it part of an even larger superstructure? Or is it a unique, rare, cosmic accident? We don't know yet, but what we do know is this. The discovery of the Einasto Supercluster has changed the scale of what we consider possible. It reminds us that our map of the cosmos is still under construction. Each new observation redraws the edges. Each new structure rewrites the scale. Cosmic humility. There's something deeply human about making maps. We map mountains, we map oceans, we map stars. It gives us a sense of place, of orientation. But every once in a while, a discovery reminds us how unfinished our maps really are. Einasto is one of those discoveries. It tells us that the universe is bigger, more connected, and less understood than we assumed. And it invites us to look again, not just at the data, but at our ideas, at our confidence, at our humility in the face of something far greater than ourselves. In the final chapter, we'll step back and reflect. What does this mean for humanity? What does the existence of a structure like Einasto tell us about our future in the universe? And perhaps most importantly, are we standing on the edge of something even larger? Chapter 5. What comes after the edge? Let's imagine something. You're drifting in space. Behind you, the Milky Way, La Niña, all the stars you've ever known. Ahead of you, darkness, expanding faster than light, filled with secrets we haven't yet named. You pass galaxy after galaxy, cluster after cluster, and then far in the distance you reach it. The Einasto, a continent of galaxies, a gravitational ocean, a silent monument stretching across more than 1 billion light. And even then, even in the presence of something that massive, You feel a strange pull not toward it, but beyond it, because something in your mind still whispers. What comes after this? The edge that is an Einasto may be the largest fully defined structure we've ever mapped. It may be the most gravitationally cohesive supercluster we've observed, but it is not the edge of the universe. In fact, it may not even be close. The observable universe spans over 93 billion light-years across, and we've mapped only a fraction of it. Structures like Einasto show us that the universe still has surprises hidden in its depth. If something like this exists here, then what might be waiting out there, beyond what our instruments can currently see? The truth is, we don't know. But that's not the end of the story. It's the beginning. A living universe, still building itself. One of the most important lessons from the discovery of Einasto is that structure is still forming. Despite dark energy pushing galaxies apart, despite the cold silence of cosmic void, despite the idea that the universe is slowly drifting into entropy, there are still places where gravity wins, where galaxies are pulled together, where motion, energy, and transformation continue. Einasto isn't a relic, it's alive, and that tells us something powerful. The universe is not finished, not quiet, not settled. It's still becoming a mirror for ourselves. Why do we care so much about something billions of light-years away? Because in a strange way, structures like Einasto help us see ourselves more clearly. They remind us that we are not alone, not just in space, but in time. We are part of a story that began long before Earth and will continue long after it. The atoms in your body were forged in stars. Those stars formed in galaxies. Those galaxies gathered in clusters, and those clusters are drawn along the invisible threads of something vast, something like To study the largest structures in the universe is to trace the lineage of our own existence. We are small, yes, but we are connected to everything. Future eyes on the sky. The next generation of telescopes will look farther and more clearly than ever before. The Euclid Space Telescope, launched to map dark matter and dark energy, is already delivering data that may confer more expanded understanding of structures like The James Webb Space Telescope, with its deep infrared vision, continues to peer into the earliest stages of structure formation. And on Earth, massive surveys like Vera C. Rubin Observatory's LSST will scan the entire southern sky every few nights, mapping billions of galaxies over the next decade. These tools may help us find more superclusters, more spines in the cosmic web, maybe even something larger than that. But even if we don't, what we've already found is enough to reshape how we think. What comes after the edge? Maybe it's more matter, more structure. Maybe it's nothing, just dark energy and silence. Maybe it's something else entirely. Maybe we're looking at the wrong question. Maybe the edge isn't out there. Maybe it's within USA's limit of imagination, a border drawn by what we expect, rather than what is. The discovery of the Einasto Supercluster pushes that border. It invites us to ask questions we once thought were answered, to redraw maps we once believed were finished. And in doing so, it invites us back into wonder. Because the universe isn't just expanding in space, it's expanding in meaning, a quiet call to curiosity. So here we are, on a small planet, around a small star, inside a galaxy that's just one of over 100,000 in our local and somewhere out there, 3 billion light-years away, the Einasto Supercluster spins in silence. It doesn't need us to notice it, but we did. And maybe that's what matters most, that in a cold and vast universe, we're still looking, still mapping, still wondering, still reaching past the edge. If this journey through the cosmos sparked a thought, a question, or a sense of awe, let us know in the comments. We explore stories like this every week, one discovery at a time. So if you'd like to keep going with us, don't forget to like, subscribe, and share this story. Your curiosity keeps this universe alive.